Let's now set forth doing the actual calculation in the case of coin tosses. So to recap, you have a coin whose bias is some p. The null hypothesis is that p is smaller than or equal to 3/4. Okay, they decided to use the test statistic t, which is you do 20 tosses, and t is the number of heads that you observe in these tosses. The test that we would like to do is test if t is more than c, right? And as I said, the reason you'd like to do this is because you'd like to reject the null hypothesis. And if p is smaller than or equal to 3/4, then a good way to reject something like that is to see if the number of heads is way too high, right? So if p is 3/4, you expect 15 out of 20 to be heads. But if it's, let's say, 19 or 20, if the number of heads is like 19 or 20, then you may expect that the null hypothesis is false. Okay, so let's see how to find ways of how to actually do computations with this. Okay, so this is the standard principle, the standard routine you need to follow. You have to compute the probability of test is successful conditioned on the null hypothesis, right? So how do you compute that? So let's say the coin has bias p, and let's say the test has this form t. You check if t is more than c. Then what we are interested in is probability that t is more than c. Note that we have seen this t is a binomial distribution. Okay, so we've seen this multiple times in the course. So the probability that t equals k for any k would be 20 choose k times p power k times 1 minus p power 20 minus k. Okay, and the way you get this is by saying that if I want the number of heads to be exactly k, I pick k out of the 20 positions. There are so many ways of doing this. Once I do that, there's a p to the k times 1 minus p to the 20 minus k probability that those k are heads and everybody else is tails. Okay, so that's why I get this quantity. Okay, so now if I have this for probability that t is equal to k, now what is the probability that t is more than c? This is simply probability that t equals c plus 1 plus probability that t equals c plus 2 plus so on. It's probability that t equals 20. Okay, so that's the probability that t is more than c. And we can now evaluate this probability, right? So you can plug in this formula and you get something, right? Now you can write down an expression for it, but to actually evaluate it, you need to know p. Okay, in the sense that even under the null hypothesis, if I assume that p is smaller than or equal to 3/4, maybe this value depends on the actual, this value actually depends on the value of p, right? But one thing that I will claim here, and it's intuitively a very simple claim, is that it is enough, or rather to bound, to obtain an upper bound on this probability. Let me call this star for now. On star, it is enough to consider p equal to 3/4. Okay, so what this claim is saying is that if I want to remember, what I'm ultimately interested in is bounding the probability of the success of this test under the null hypothesis, right? So I don't need to exactly compute this quantity. It's enough if I say that this quantity is, let's say, less than or equal to 0.05 or something like that, right? So all I need is an upper bound in that sense on this quantity, which is probability of test being successful given null. And so for that, I need an upper bound on this quantity, right? Because this is exactly equal to the top one. And what I'm claiming is that if the higher the p, the higher this probability gets. Okay, and this is intuitively obvious. If you fix a c, right? If I fix a c and I say that what is the probability that more than c out of the 20 tosses are heads? Okay? Now, if my coin is more and more biased, this probability only increases, right? So this is a very believable claim and it can be proved formally. So I won't actually prove it because I don't think it's very important for us. But this claim holds. Okay? So the bottom line of that is that I can now evaluate this probability by plugging in p equals 3/4. Okay, so from now on, let me plug in p equals 3/4 to reason about the null. Okay, so I need to evaluate quantities like this for p equals 3/4. Okay, now how do you do this? I mean, thankfully, we don't have to compute a messy expression like this. R has a nice function that computes the density function of a binomial, and this is called the d binom, right? So the way you plug this in is you give k, you give n, and you give the probability p, okay, of heads. So here are the values that you get. So if I want probability that t equals 20, then that's this number. Probability that t equals 19 is this number, t equals 18 is this number, and so on. So now, suppose I choose, actually let me insert a new page here. Okay. So say we choose c equals 19. Okay, that's like saying so then test succeeds if t is more than 19, or equivalently if t is 20, right? Because there's only one value of t, one possible value of t that is more than 19. T lies between 1 and 20, 0 and 20. Therefore, there's only one value more than 19, which is t equals 20. And so the probability of this, t more than 19 under the null, okay, I've already told you that instead of under the null, I could just say that this is equivalent to saying p equals 3/4. Okay? So this is always less than or equal to this value, right? So this is the value I obtained by plugging in p equals 3/4 and x equals 20. Okay, so that's like 0.0032. Okay, so that's about 0.32%. Okay, so this is a really tiny value. Okay, but this is nice because what it's saying is that if I choose c to be 19, that is, I accept the test only if all the 20 coin tosses ended up being heads, okay, then under the null, which says that that p is smaller than or equal to 3/4, this is a super low probability. Okay. Now, what is the bad thing about this test, right? So the good thing about this test is that, so this is a useful trade-off to understand. Good thing about the test is that you will almost never accept the null hypothesis. So you'll reject the null with a very high confidence. Okay, and if you remember, this is the quantity that we defined to be the significance level, right? So the significance level of this test is extremely high. So what is the bad thing about this test? So the bad thing about this test is that you even if you may reject things that are not the null, right? So let's say p was 0.8. Okay, so if you evaluate this quantity, this will still be kind of low. Okay, so you will pretty likely reject this value of p also. Okay, and that's the kind of trade-off that you get if you want a extremely high likelihood test. Okay, that if you have small number of samples, in this case you only have 20 samples, and if you want to reject the null with a very high confidence, then you may end up rejecting things that are not the null also. Okay, so that's one trade-off to keep in mind. Okay, so in fact the way to fix this, so there's a more sophisticated test that we will not look at in this course, but for those of you who are interested, you should look at, so there are lots of statistical tests, and one of them is called Neyman-Pearson test, which is a more sophisticated way that takes into account this kind of a phenomena. There's also this thing called a likelihood ratio test, which also captures things of this nature. Okay, so let me not go more into that, but this is one thing for you qualitatively. You should know that this is an issue with tests, right? Like if you have a test that is too strong in some intuitive sense, then you will reject the null with a really high probability, but you may end up rejecting things that are outside the null as well. Okay, so that's some stuff to keep in mind. Okay, so this is the calculation when c equals 19. Now what happens when we choose c equals 18? Okay, that means this is equivalent to saying that accept if t equals 19 or t equals 20. Now what's the probability of that? Probability that t equals 20 is this, which we've already computed. Probability that t equals 19 is this. So the sum of these two is roughly 0.24. Let me write 0.24. 0.024 rather. So probability of test succeeds given null is less than or equal to 0.024, which is about 2.4%. Okay, and if you go one step lower, you go to say c equals 17. So now you've got to add up the first three quantities. Okay, then you end up with a probability of roughly 0.08. Okay, so this thing is roughly 8%. Okay, so if you chose c equals 17, then your probability of rejecting the null, okay, which is what we defined to be the significance level of the test, okay, so that becomes a bit higher, right? So that becomes 0.08 or 8%. Okay? While if you're stuck with c equals 18, your probability of rejecting the null is quite high. I mean, the probability that you accept it is only like 22.4%. And like I was saying, p equals 0.05 is often the accepted threshold, or 5% is like the accepted threshold in many applications. So this is not a good value, while this is actually a decent value. Okay? So in this case, you might decide to go with c equals 18, because it's not as strict as c equals 19, where your probability of rejecting was extremely high. Okay, so rejecting the null was extremely high, but you might also potentially reject other stuff, okay, like p equals 0.8. So here, if you compute p equal the value, this is a good exercise for you. See what happens. Well, for p equals 0.8. Okay, so you will see that the value is significantly higher. Okay, and that's what motivates tests like this likelihood ratio. So okay, so that's the idea here. Okay, so if we are if we want a high confidence, or if we want the probability of rejecting the null to be very high, then you'll have to, the right C to choose is C equals, oh sorry, I should have written C equals 18. Okay. So this is how you do these calculations. Okay. Right, so let me come to a quick summary of hypothesis testing in the next video.